Welcome to the Leap Australia tutorial for Pyfluent simulation setup for FSAE. This tutorial will cover the setup script, how it works, and required changes for new geometries. With a successful mesh generated, the setup script can now be used to perform the simulation setup prior to running the simulation. Simulation setup is much faster than meshing. It involves specifying the viscous model, simulation type, boundary conditions, moving ground and rotating wheels, output monitors, and run duration. If simulations have never been run in Fluent before, the linked video provides a comprehensive tutorial on setting up simulations in Fluent and will help with understanding how the script functions and possible problems that may occur. The script does not adjust the reference values for the simulation, and so coefficients are computed using the default reference values.
The coordinates for setting rotating wheels in simulation setup can be found during geometry preparation in SpaceClaim. This can be found by hiding the bodies of influence and hiding the enclosure faces. Then using the design tab and selecting each side of the wheel, you can insert a coordinate axis for each wheel, as so. These coordinate axes can then be used to find the coordinates for the front and rear wheels. This can be found by using the measure tool, selecting the global coordinate system, control clicking and selecting the firstly the front wheel. You can check the show XYZ vectors box on the left and change the units to meters, and then these coordinates over here can be inserted into the setup script to tell Fluent where the front wheel rotation axis is. The same procedure can be used for the rear wheel by selecting the global coordinate system, control clicking the reference coordinate system, measuring, and then using those values over there to put into the setup script for the rear wheel. For more information on finding the rotating wheel coordinates, the linked video in the slide will show this process in more detail. Like the meshing script, the setup script also makes use of global variables to allow for quick and easy editing of things like simulation velocity, wheel radius, the front and rear wheel rotation coordinates, the number of iterations, etc. This also includes the save directory, which would be the same folder as specified in the meshing script, as well as the names used when saving the setup file and the results file. It also includes the mesh file that needs to get called in by the setup script in order for setup to be completed. Just like Fluent in meshing mode, Fluent can be launched in solver mode using various different settings like double precision, process account, and also the show GUI option. The process account is the most important here for solving. Just remember to set this process account value to what is allowable by your license and also by your PC. For the purpose of this tutorial, it can run perfectly fine on a process account of 6, but obviously this can be increased to allow for the simulation to be solved faster. The generated mesh file from the meshing script is then read in and checked again to ensure it is valid. The setup section of the setup script now begins with enabling the viscous model. For this tutorial, the viscous model is set as K omega with shear stress transport and curvature correction set to true. The inlet boundary condition is then defined. This involves setting the inlet face velocity to be equal to that of the simulation velocity specified up at the top. So in this case, 16.667 meters per second or 60 kilometers per hour. This also sets the inlet boundary condition with an intensity and viscosity ratio of 0.05 and 10 respectively. The outlet boundary condition is then specified with 0 pascals relative pressure. The wall boundary conditions are specified as stationary walls with a specified shear value of 0 pascals to allow slip at the walls. The moving ground boundary condition is then specified with a velocity equal to the negative sim velocity as the ground moves in the negative direction given our global coordinate system. If you would like to change the moving ground velocity to be different to that of the global variable specified above, this value over here can simply be changed to say 15 meters per second if you were wanting to simulate a headwind or a tailwind, for example, to have a moving ground velocity different to that of your inlet velocity. The front and rear wheel boundary conditions for rotating wheels are then specified. It is important to make sure that you change the rotation axis origin and axis directions to match your geometry. Also make sure to accurately set the rotation axis so that the wheel is rotating about the correct axis in the correct direction. So to specify the rotating front wheel, it is set as a moving rotating wall with a rotational velocity set to the simulation velocity divided by the rear wheel radius to calculate the rotational velocity of the wheel. The axis origin is then set at the front wheel X, Y, and Z rotation coordinates specified above, and the rotation direction is set to rotate around the y-axis, which is the axis of rotation for the wheels for the chosen global coordinate system for this tutorial. The rear wheel boundary condition is then set in exactly the same manner as the front wheel. With all the boundary conditions set up, report definitions for lift and drag can now be created to monitor the process of the simulation and view the downforce and drag as the simulation runs. The lift and drag definitions can be calculated on the whole car or just a certain component, depending on the named selections in the zones specified. For this tutorial, the lift is defined in the negative Z direction, over there, and the drag is defined in the negative X direction, over there. So depending on how you would like to change the calculation of the lift and drag report definitions, or like which surfaces these are calculated on, this can be specified by changing the named selections in the zone list over here. For further monitoring, report plots and report files can be used. The report plots will plot the lift and drag values for each iteration, while the report files will print the final results to a text file at the end of the simulation. The residual plots are also set to local scaling in this step over here. The simulation is now almost ready to be run, but first the solver must be initialized, and then the case and data files are then saved to the save folder specified at the start of the script. Once this has all been completed, the simulation can now be run. The script will then begin the simulation. The simulation will be run first for half the iterations to reach a semi-converged state, after which steady statistics will then be set to determine a mean of the results. The simulation will then be run for the remaining half of the defined iterations where these steady statistics will be determined and can be analyzed during the results post-processing. The simulation is complete and the results will be saved. If you do not want the simulation to start automatically, because you would like to catch any errors before you start the simulation, then this block of code over here can be commented out using triple quotation marks like this, which means the script will not automatically start the simulation. What you can then do is allow the script to set up everything for you, and then you can manually start the simulation when you're ready.
Now that the simulation is complete and the results have been saved, the results can then be post-processed. The post-processing of the results is not detailed in this tutorial, but 2 Ansys tutorial videos showing post-processing within Fluent are linked on the slide and will provide everything required to start post-processing the results. Thank you and all the best with your Pyfluent simulations.